just occurred to me now that.
Thank you.
Is it recording?
It's recording now. Yes, recording.
It's
yes.
recording. Okay. Thank you. Good.
Continue.
So, sorry for the brief interruption. I just wanted to be sure that we're having this on record. So I was saying that for those of us that might be looking for better job opportunities in the energy industry, the renewable energy industry, this is a very good opportunity for you to grasp a good understanding of the solar PV system. Solar system is not the only renewable energy source. We'll get into that detail in a little bit, but not into full detail. We just discuss about it, then we'll move ahead to the solar PV system, which is our main focus for this training. Then for some of us who might be having the ambition of starting our own businesses in the renewable energy sector and perhaps the solar system, this training will give you a very good understanding of how the system works, how the technology works, and how you can best apply what you've learned in providing solar system for homes and businesses. So your feedback is the feedback of the participant will be considered, and the training material can be modified, or new slide may be added at the end of the training. Participant will get the modified material. I think Inclination has said something about this. As we proceed with the training, it is anticipated that maybe at some point we might need to add more information depending on the level of feedback or the interaction that we have. We might feel the urge to add more information on the material. And if in the event that we do that, we'll eventually share the material with every one of you to have a complete information. So please don't be formal and cooperate actively. Your feedback is highly welcome. Please, if at any point in time you have a question, feel free to unmute your mic and then ask your question. You can as well drop your question in the chat box. Someone, I think there's Engineer, are you there?
Yeah, I'm here. I'm here.
Yeah, please, if you're here, please just kindly keep looking out on the chat box and see if there are messages that I'm supposed to respond to, so that I can focus more on the training. Yeah, exactly.
Okay.
Thank you.
Continue, please.
Yeah. So before we jump into the main topic, which is the solar PV system, I just want to do a brief recap of the energy system, the sustainable energy system. This is part of the training that we had, the first training we had on energy auditing. So I feel it's very important just to have a brief recap so that we can all understand the subsequent slides that we'll be talking about. So this is just a snapshot of what a sustainable energy is all about. Sustainable energy is basically about two things: energy efficiency and renewable energy. So first of all, we're talking about sustainable energy. The first thing that comes to mind is to reduce your energy consumption. Bear in mind that the best form of energy is the one that you did not use, the one that has not been, if I don't need to use, that's the best form of energy. So the first thing in sustainable energy is to first of all reduce your consumption, and then the next stage is to now generate your required energy consumption from a sustainable source, a renewable source. Okay, it is assumed that renewable sources are the most sustainable energy sources. So in that regard, it's expected that you first reduce your consumption, then you then transform your generation to a renewable energy source, which cannot, of course, get depleted. So the energy itself, the word energy has its origin from the Greek word energia, which means activity or drive or vigor or force, or power or strength. So I mean, all of this is just a symbol of what energy represents. So it is a capacity to perform work or heating or cooling. So whenever you do any work or you do any heating or you do any cooling, you are using energy. If you don't use energy, none of those things is going to happen. So energy is one of the most important concepts of natural sciences. Nevertheless, it is very difficult to define in few words. So why do we need energy? The basic need of energy is simply, now these are more like the family or the residential home need. You need it for preparation of food, you need it for heating, cooling, personal hygiene, lighting, and then of course, every other work that you need to do. Then at the industrial level, you need it for production. Every product that you see in the market has undergone through a kind of reformation processes with the use of energy. So you also have transportation. You need to move from point A to point B. It won't be possible if there is no energy involved. So in terms of production of goods, commodities, energy is all needed. In fact, without energy, I don't think everybody will just be, you can't even do anything. You can't breathe. So energy is all over, it's all around us. So we have different forms of energy, okay? You have the mechanical energy, you have the thermal energy, you have electromagnetic energy, you have electrical energy, which every one of us is very familiar with. And it's more like the best form of energy, because from electrical energy, you can literally convert any other form of energy, which makes it the most viable form of energy. Then you have chemical energy, then you have nuclear energy, okay? So the applications of these forms of energy are also listed here. You can always make reference to this at your own time. So energy sources and the law of energy conservation. So the primary source of energy is from the sun, and from the sun, it's the trees, the plants and trees convert this energy into other forms of energy. Basically, the food that we eat through a process known as photosynthesis. We all did this in our primary and secondary school level. So from there, we all consume this as food. And then by the time every one of us has reached the end of our lifetime, we all somehow have been buried, and then we go beneath the earth. Then it takes like millions of years for these bodies to decompose and become gas and crude oil. And of course, this gas and crude oil have been exploited through the exploration process. And then they undergo through refinery processes to get different forms of liquids, even solid form of fuel. You have the diesel, you have the petrol and stuff like that. And the basic need for having all of these processes to power our economy. The vehicles that transport people to point A to point B needs those kind of fuel to function. The industry, the generators that run need those kind of energy to function. So now our focus would be on renewable energy, and we want to see how we can take it straight ahead from the sun. So it doesn't need to undergo through all of these processes. If we can harness this directly from the sun, then that will be a better option instead of going through all of these processes and then coming back to fuel our economic activities. And here is the problem. The sun already has sufficient energy to power all our activities on Earth, okay? But because we lack the technology to harness it and convert it to the form of energy that we need, we have to now go back and then exploit the energy that has been sequestrated, the energy that has been stored beneath the earth by the act of divinity. So by the time we explore them and we introduce them back to the earth, and then combined with the energy from the sun, we begin to heat up the planet. And this is the major problem of the world as of today, which is global warming that eventually leads to climate change. And this is the main reason why the emphasis on renewable energy is so high, okay? So energy does not remain in the same form always. To cause change, energy itself changes from one form to another. I think I've explained all of this with the diagram already. So just to state that the law of energy conservation states that energy cannot be created or destroyed, but can be converted from one form to another. So in the actual sense, you can't create energy. You know, energy has been created by God. And you can't destroy energy either. You can only transform it from one form to another. And that's what the law of energy conservation says. So I'm going to talk about energy and power. These are two different things. A lot of people confuse this energy and power to mean the same thing. They are not the same thing. So energy is the capacity to do work, okay? And energy is equal to force times distance. So when you push a table, when you apply a force on a table and it moves, for example, 10 centimeters, then you will have dissipated energy from your body to moving that table from the point A to point B. But if you apply that force on that table and it doesn't move, you've not actually dissipated any energy. So just for us to understand what energy is. Okay, so that is energy, and energy is being measured in joule. Okay, 1 joule, okay, the definition of joule is Newton times meter. Remember when I talk about distance is all about meter and force is all about Newton. So the unit of energy is it can be joule, and joule is equal to Newton times meter or distance. So now let us look at power. Now, power is the actually energy over time. Okay. So by way of formula definition, our power is measured in watts, and watt is equal to joule. Joule is a unit of energy, you remember, and then time is a unit, is the smallest unit. Is it the smallest unit? But the smallest unit that we all use in measuring time, because I know there is microsecond and the rest of them, but in terms of second, that's the smallest unit that we all use in measuring time. So time in seconds anyway. So the unit of power is joule per second. So if you now rearrange that formula and make energy the subject of the formula, what you're going to have is that energy is equal to power times time. Power times time, and those are the units. Okay, so energy and power. Okay. So energy, I talked about the unit of energy that is in joules, and joule is actually a thermal unit of energy. But if you remember, most times the primary source of energy is usually a thermal energy from the sun, or when you're when you're burning your fossil fuel to generate power, you first of all have to generate thermal energy. So basically, energy is the primary unit of energy is joule, which is a unit of a thermal energy, but it can be converted to every other different unit. Then power is watts, measured in watt, and watt is voltage times current. I would want you to note this down. Power, which is W, is equals to voltage times current. As we proceed with this training, we are going to making a lot use of this formula. So power is just telling us how fast energy is being used. Okay, that's what power tells us, how fast energy is being used. Here is this little exercise. I don't want to waste our time on this, but it's just to test our understanding of power and energy. It's included in the material that you have. At your own time, you can just go through this so that we can proceed. We have a lot that we need to cover today. So I just did that little introduction on energy generally, and then also touched about renewable and non-renewable energy, talking about the fossil fuel, the solar, and then of course I didn't mention wind. Wind is also part of the renewable energy system. Unfortunately, it's we don't have so much wind speed in most part of Nigeria. So at the moment, solar is considered the best form of renewable energy at the moment. In as much as we've not been able to explore other forms of renewable energy, such as the hydro, maybe mini hydros, and then biogas. But technically advanced, I think solar has gone so far, and which is the reason why we want to focus more on the solar. So talking about the solar system. Now, photovoltaic PVs, photovoltaic PVs is the technology which generates electricity directly from sunlight via photoelectric effect. Now, the whole idea is this: if you can convert electric energy to light through your light bulb and all of that, then it only makes sense that you should also be able to convert that light is coming out from your bulb back to electricity. Okay, so I mean, I think this is the idea that inspired this whole technology. I mean, to reconvert light back to electricity. So now the technology that does that is what we know as photovoltaic, which is in short known as PV. So the photovoltaic module, which is made up of photovoltaic cells, transforms solar energy into DC electricity. Another solar energy technology is solar thermal. Okay, so solar thermal uses solar energy to generate heat rather than electricity. So there are two different forms of solar energy here. You have the photovoltaic, which is the PV that I talked about. Then we have the solar thermal, which is to generate heat, basically maybe to produce hot water. And this too, you can see them by the pictures. So it is important to make a clear distinction between these two different technologies, which are often confused since they use the same energy sources, which is the solar radiation. So there are two different things: solar thermal, solar photovoltaic. So the electricity generated using PV can be fed into the electricity grid. You can also store it in battery for later use, or you can use them directly. Then as of 2018, the total global installed PV capacity was approximately 290 gigawatts. If you convert that to megawatt, that is going to give about 290,000 megawatts. Now, to help you make sense of that, the whole of Nigeria is just generating about 3,500 megawatts. The whole of Nigeria, 3,500 megawatts. Just to let you know the magnitude of the energy that has been generated as of 2018 from the sun. So this is a typical example of both solar energy that I talked about. You can see a building that has solar PVs and as well as a small solar thermal that generates hot water for the home. In this case, it makes a lot of sense to have a solar thermal to generate your hot water rather than using the electricity that has been generated by the solar PV to heat your water. You're converting it back to heat. So it makes a lot of sense in this case to use your solar directly to produce your hot water. So this building has perfectly illustrated the use of these two technologies. So we're going to be talking about off-grid PV system and grid connected PV system. So now we are going through the solar PV system. We're now leaving the solar thermal aside, but it's good to understand that aspect of solar energy. So in the solar PV system, we have the off-grid application, and then we have the on-grid application. That is, solar PVs have been connected to the grid. So here is just a typical illustration of both the off-grid and the on-grid. Okay, I think I will talk about this more in the subsequent one. But if you, most important thing, if you look at what you see on the off-grid PV system, you're going to see a red box that is talking about the solar cell. Okay, so you have a lot of solar cell that comes together to form a solar a module. Okay, I think I have this illustrated in some other slide. We'll get to that. So let us talk about the PV system application. Like I said, we have the PV off-grid and we have the PV on-grid. So on the off-grid side of it, we have PV system for rural electrification, which is very common in Nigeria, trying to electrify the rural communities using solar PV system instead of extending the grid, which are not economically viable. So we're talking about rural electrification. You have the system that has batteries, okay, to store the solar energy in times when you don't have the sun, so that you can actually get back the energy from the battery and then sell to the communities. Then you have systems without batteries. So when you have systems without batteries, what that means that when the sun is not out there, you don't have any energy output. Then you have the standalone mini grid. So standalone mini grid is now whereby you have a purely PV and then you have the hybrid PV where you now combine the energy from the solar with other forms of energy, maybe from diesel generator or from the wind or from any other source. Then we have the large PV diesel hybrid mini grid. Now this is most suitable for industrial applications. We'll talk about all of this as we proceed. Then on the PV grid connected solar system, we have the distributed PV system that is feeding into the low voltage network. So example of this is residential rooftop, and they have commercial or industrial, maybe rooftop or even if it's on the ground. But the most important thing here is that you're feeding into a low voltage distribution network. It's not common in Nigeria because we don't have a stable grid. Okay, what we basically have in Nigeria is a PV off-grid. But it's also important that we talk about the PV grid connected because it's becoming a possibility in Nigeria. We'll go into all of these details. I will go into this training. So we also have a central PV system that is feeding onto the medium voltage grid. Okay, now this is a central generation using solar PVs, and then you're feeding into a medium voltage that can now be sold maybe by distribution company, regular distribution companies that you know today. So you generate at a certain point, just like your regular power plants, like your hydro or your thermal power plants. Then you feed into the transmission system, then of course to the distribution system that now sells to the homes. So in that center, you have the large-scale PV power plants. So just for us to have, this is the kind of categorization of the solar PV system. You have the on-grid and you have the off-grid system. So now I'm going to talk about the grid-connected PV configuration. So I kind of explained this in the previous slide, whereby you have your solar PVs and then you connect to a low voltage network, okay? So distributed PV system can have various sizes and will be located at different points in a central electricity grid. Distributed systems are typically constructed on residential, commercial, or industrial buildings. Systems on residential buildings are usually small rooftop systems generating electricity for private consumption or for sale to the electricity utility. So if you look at the diagram by the left, you see that you have your solar PV, rooftop mounted solar PVs. Then you have your junction box that connects all of these cells together. Then you have your inverter that converts from DC to AC. I hope we all know that the solar PV generates electricity, the DC type of electricity. Okay, so you need an inverter to convert it from the DC to AC that we all use in our various homes. So once that is done, then you have a meter that actually meters what you're sending to the grid. Because in the developed country, where this is very, very practicable, when you sell this electricity that is generated from your rooftop to the utility companies, they actually pay you for it. Assuming you don't take it back from the grid, they pay you for it. But if you sell to them, so for example, if you give them, for example, if you give them 10 units, and you for collecting 2 units extra, and we call that net metering. Net metering. At some point, when you start having conversation around the energy system, you might begin to come across the word net metering. That if some of you already are not familiar with it. So this is what net metering is. And a lot of countries has actually deployed this technology, you know, in a very wonderful way, especially Germany. So this is what grid connected home PV systems. This is what it looks like. So systems on commercial and industrial roof are also used to either offset on-site generation, on-site electricity consumption, or to sell electricity to the utility. However, commercial/industrial systems are often much larger than residential systems. I think I've discussed some of these things. So in all grid connected systems, the PV array is sometimes referred to as the solar generator. Okay. Now the figure you're looking at is a typical residential PV system. Now, like I explained, it generates what we know as DC electricity and is connected via a junction box to an inverter, which converts the direct current into an alternating current. Now, the inverter output is connected to a meter, which records the amount of energy being fed into the grid. Now, this is just to reiterate what I've said previously. So you have the grid connected configuration. In this case, you now have a central PV system. Now, I also make a little remark about this. So central PV systems are also known as solar farms. Either solar farms, solar parks, or utility scale PV system. So large scale PV power generation is concentrated at one specific location. Just like your normal, maybe hydro power station or thermal power station is concentrated in one station, then such plant can take up large area of land and feed directly into the electricity grid. The configuration of such plants is more comparable to conventional power plants, producing 3-phase power. They are connected in medium or high voltage transmission network. I already explained this. So this is just a schematic of what a grid-connected PV system looks like. From your solar panel to an inverter to energy meter, then of course, then you fix your grid. This is a fuse that prevents backward feed, I guess, or high voltage as well. If I think if there is the fuse does a lot of things in terms of protection. So now let's talk about the off-grid configuration. Off-grid PV systems are not connected to the electricity grid. They are also called standalone PV systems. The electricity produced is consumed very close to the location where it is generated. Off-grid systems usually incorporate battery storage so that electricity can be supplied even when the sun is not shining. Solar water pumping systems are a major exception to this. Okay. So solar water pumping system is, for many applications of solar water pumping system, you don't have storage so that water can only be pumped when the sun is shining. But this is quite different from off-grid PV configuration, whereby you need to have a battery storage so that when the sun is not shining, of course, you still need to carry out your activities in the house. You need energy. So you use battery to store the energy while the sun is shining. Off-grid systems are usually found at locations where there is no electricity grid available. The system component differs from grid-connected system, and the array size is typically much smaller, especially for small off-grid applications like solar home system. So the PV modules are connected to charge control. They are connected to a charge controller. We will talk about all of this as we proceed, which regulates the charging and discharging of the batteries. Only DC power is supplied. Many of these systems also have inverters connected directly to the battery, which supply AC power. We'll talk about inverters as well. So these are off-grid configuration. Now this is for a central generation like a mini grid or a microgrid. Okay, so this is not okay. So a micro or mini grid are basically small electricity grids providing electricity to, for example, a small island or remote building complex or a village. This is an off-grid configuration, but again, it has its own grid system, which is a mini grid system or a micro grid system. Here we are classifying them as an off-grid system. They usually have backup power sources, most commonly a diesel generator. Most commonly viable is a diesel generator. However, for some applications, you're going to find that we don't have diesel generators. We have battery backup storage instead of diesel generator. Now, the reason why diesel generator is most viable is because of the cost of batteries. The cost of batteries is so huge compared to diesel generator backup. So some larger micro or mini grid systems do not have battery storage. So electricity is typically produced and stored at a central point from which it is distributed at AC grid voltage. So let us look at the components of the PV system. So now we're going to look at different types of PV cells. As we all know, the primary element that generates this electricity is the PV cells. Okay. So we have about three common types of PV cells. Okay. So the PV cells is the core components of PV system since it generates the electricity. There are many different types of PV technologies, but the market is dominated by crystalline silicon based PV cells. Nearly 80% of the cells on the market are crystalline silicon based cells, either monocrystalline or polycrystalline. Now, the remainder of the market is taken by thin film modules. If you look at the table that I have here, you see monocrystalline silicon-based PV cell. You see polycrystalline. So this is monocrystalline, this is polycrystalline, and this is thin film. If you look at the panel efficiency, you see that the polycrystalline has an efficiency of about 18%, while the mono has efficiency of about 22%, and then the thin film has 17%. Look at the power temperature coefficients. What this means that for every rise in temperature, the energy output, the power output drops by minus 0.4 to 0.5. That's what this coefficient. We'll talk about them in detail. But you can see that this one has a slight bit for every rise in temperature, it loses more power compared to monocrystalline and as well as thin film. But the surprising thing is that when you look at the market share, you will see that the polycrystalline has a larger market share, followed by the monocrystalline. Whereas their efficiency output, the monocrystalline has 22%, and the polycrystalline has just about 18%. So the question is, what could be responsible? The thin film is not preferred in the market, and you can see it's about 5%. The main focus here is on the monocrystalline and the polycrystalline. In as much as the monocrystalline has higher panel efficiency, it's still not doing very well in the market. Now, the point is this: the price difference between monocrystalline and polycrystalline is so much that it is not worth this 4% difference in efficiency. If you notice, the difference in this panel efficiency is 4, but the price difference is not worth that 4. So it's better I just go, because this polycrystalline is far cheaper than monocrystalline. So, and I can't just use because of 4% and then go for something that is very more expensive. So that explains the reason than the monocrystalline. If anyone has questions, please do ask. If you have contributed in this, I'm just glad that if you that is important, please let me know, and I'll give you the opportunity to talk. So, selected technical characteristics of silicon wafer-based and thin film-based panel. Okay, that's the table you're seeing above you. So now let's talk about the PV modules. Now remember, we'll talk about the PV cells. Now, when you combine the PV cells are formed by connecting sorry, I take that again. PV modules are formed by connecting PV cells in series or in parallel and encasing them in a protective material. Okay, so I remember I talked about the PV cells. Now, what we often hear in the market is PV module. So PV module is now a combination of several PV cells connected either in parallel or in series. Okay, so that's what forms the module. So PV modules can also be connected in series and or in parallel in order to form what we call the PV array. So if you look at the rooftop here, what you have is PV array, and it's a combination of several PV modules. Combination of several PV cells will give you PV module. Combination of several PV modules will give you PV array that I will say here. So the number of modules determine the maximum power generation capacity of the plant. Of course, the higher the number of modules you put, the more the output from your plant. So this is at the PV module level. Remember, we're talking about the components now, and the primary component here is the PV cells, which when combined gives you the PV module and of course the PV array. Now let us look at what happens when you generate power from these PV modules or the PV arrays. When you generate the power, an inverter converts direct current. Now remember, when the power is coming out, it's coming out in the form of DC. So the inverter converts it from DC. An inverter converts direct current input from a PV array or a battery into an alternating current. So if you look at the diagram, you have the sun radiation, then you have the solar array, then you have the inverter, and then you're feeding into the grid, assuming it's a grid connected system. But of course, you know you're going to have a meter somewhere here to meter whatever you're feeding into the grid. So the PV modules produces only DC. However, electrical energy is usually transmitted and distributed in AC forms. And most appliances are types of inverter. Now we understand what inverter does. I know most of us have this knowledge already, but for the benefit of those of us who are not very conversant and familiar with this, please let us just take it slowly. Okay, we'll get to the a more technical side of it. So there are three different sizes of inverters. So first of all, you have a micro inverter. Micro inverters which are directly connected to a PV module, e.g. up to 300 watts. Now, remember I talked about the PV module. Now, if you have an inverter connected directly to the PV module, so that whatever electricity in form of DC that is coming out from the PV module is converted to AC directly at the module level, that is micro inverter. Okay, so the next type of inverter, we have strange inverter. Remember I talked about arrays, solar arrays. Now, it is possible to have maybe 3 or 4 solar arrays. Now, each one of those solar arrays is what we call strange. Okay, so you can have a combination of maybe 10 solar modules to form one array. We call them string in this time, and then you have one inverter connected to it. Then you can have another 10 solar modules form another string. Then you have another inverter to it. Okay, so now this is string inverter which are connected to one or a few strings of PV modules. Each string can have up to 20 modules, as the case may be. So this is a size of inverter that is connected at the string level. Then you have a central inverter which are used in large PV parks of several megawatts, because many strings can be connected to the inverter. So you can just connect as large as possible as solar modules, that you connect all of them to a single inverter. Okay, so these are the 3 sizes of inverter that we have.
Hello, Chima, please. Somebody is asking about a deeper explanation of the inverter system, about the micro, the string, and the central inverter.
Okay.
Maybe the micro might come in sizes also. Maybe there are some now people have in their home, which is visible, and there are some they don't see, especially in some systems like street lights. So maybe just explain more to him.
Okay. Thank you very much for bringing that. I didn't want to delve into so much of the details, but now that you're asking, let me throw more light to this. Now, there is a problem with shading in solar systems. Okay, if you have, so let me use this string. Okay, let me start from the central inverter. Assuming you have 100 PV modules connected to this inverter. Okay, sometimes some of the modules in the market, if depending on the configuration, depending on how you connect these PV modules, okay, for some of them that are mostly configured to in series, what actually happens is this: when one of the modules begins to, if there's a shading on one of the modules, so the performance of that module, if it reduces to 50%, what actually happens is that the efficiency or the performance of the 100 of them will be reduced to 50%. Okay, so that is the shortfall. That is the disadvantage sometimes of central inverters. Okay, if one of the modules have problem, there is shading on one of them, or there is dust covering one of them, and the performance drops, the performance of every one of them will automatically drop to the performance of that one that is partially shaded or that has dust covered in it. So it becomes a problem. Okay, that's one. Then if you now look at the string inverter here, okay, you have a certain number of modules connected to one inverter. So using string inverter, you avoid this problem partially, not completely. You avoid it partially. So if you have 100 solar panels and you connect them 20, 20, 20, meaning that you have 5 strings, and you have 5 string inverters. If one of them have shading or one of them has dust covered in it, it's going to reduce only the performance of the 20 that is connected to the string. The other ones can then continue to perform optimally. So you find out that using string inverter, you solved this problem, but partially. And that is where micro inverter comes to play. If you have a micro inverter attached to every one of the panel, if one of the panel has a problem, it has a shading, or there is dust covered it and the performance drop, it does not affect any other panel. It's only this panel that is affected. Okay, so now these are the disadvantages and advantages. I didn't want to go into all of this detail, but now that you've asked, it's good that I explained this. Okay, if anyone has further question or you feel that you're still not clear about it, please let me know. But I try as much as possible to make this explain this in a basic form that we can all understand. Now there's another thing that we call power optimizer. There are now, because of this problem that I just talked about maybe one solar module having problem and affecting every other module. There are different ways to deal with this, apart from this inverter that I just discussed about. So it's beyond this inverter. Now there's what we call power optimizer. Power optimizer is not an inverter. It's similar to micro inverter, but it only conditions the output from the module from DC to DC. It does not convert to AC. It only condition is from DC to DC, such that if there's a problem in this module, in one of the modules, it does not affect every other module. So if you have power optimizer, you're still going to need your string inverter, you're still going to need either your string inverter or your central inverter. I hope that's clear enough. Okay. Some other people has also found a way to deal with this partial shading in solar system. Okay. There's a kind of a diode that some people also integrate, to so that the core performance on one solar panel does not affect the other. But what I've just explained are the general basic way to look at these inverters. Remember, I have gone beyond inverter this time around, and I now started talking about power optimizers and some other things. Now, those are different ways people can handle this problem, but they are for more highly professionals. At this level, we just have to deal with this problem with the inverter at the inverter stage. So we've talked about the modules, we've talked about the inverter. Remember, the power comes from the module, it goes to the inverter that converts it to AC current or AC electricity form of AC. So now let's talk about the mounting structure. The fundamental requirement of mounting structures are that they must support the weight of the PV modules. You must understand that the PV modules has weights, okay? So as an engineer or as a technician, we must be professional. So when you're placing the PV module, make sure that the structure is strong enough to support the weight that you're putting on it. Otherwise, you can collapse a building. So they must distribute the load evenly onto the roof / ground, the ground below. And they must withstand expected extra loading. Example, from the wind or the snow. So if you're designing for a snowing country, maybe Europe or America, you must also understand that if you put your PV models, in addition to the weight of the PV models, during the winter time, the snow will also come down on the PV model and it will add to the weight. And if you don't put all of this into consideration, it may affect the structural integrity of the building. So it's very important that we consider all of this. So since large array structures, including the modules, are heavy, it is necessary to seek the advice of a structural engineer prior to roof mounting. The structure should have optimum orientation and tilt angle. We'll discuss about this. So to maximize power output and all shading, shading should be avoided. So it's saying that all shading should be avoided if you want to maximize the power output. Now, the structure will typically be made from aluminum or galvanized steel. Painted steel and wood are also options, though such structures will probably require more maintenance over the 20+ year lifetime of the system. You remember that this PV system, the PV cell, these PV models has a lifetime of over 20 years. So you must put that into consideration. So here is just a pictorial view of the mounting structure. So I think I talked about, okay. So solar panels can be installed on fixed support or on trackers. You can install them on a fixed support, no movement, is just there, but you can as well install them on a tracker, meaning that they can actually somehow follow the sun, at some certain time. So fixed support are most often directed towards the south in the northern hemisphere and vice versa. I will explain this further in the training. So trackers are motorized structure that follow the path of the sun. I already talked about this. So if you have tracker, if you install your PV system on a tracker, you remember the sun rises from the east and it sets in the west. So if you for optimal performance of your PV system, if you put it on a tracker, what that means that As the sun is rising from the east, your solar PV system is following the sun until it sets in the west. So it captures the maximum amount of electricity or energy it can get. But of course, it comes at a cost. It comes at a price. So it's not left for you, who is a designer, to do your cost-benefit analysis and then consider if it is worth, the extra cost. If you remember when I talked about the efficiency of the PV between mono and the poly, the economist has done the evaluation, and they found out that the 4% difference in efficiency of the mono is not worth the cost. And that is why the market share of the poly is almost times 2 greater than that of the mono. So in as much as you're doing all of this design and calculation, you also have to look at cost benefits. In the next training that's going to come next month, Engineer Uche is going to deal more on cost benefits and cost calculation and all of that. He's going to do more extensively on them. So trackers are motorized structure that follow the sun, the path of the sun. I already said it. So you have the single axis tracker and you have the 2-axis tracker. So the single axis tracker tracks the sun east to west, rotating on a single point, moving either in unison by panel row or by section. Now it depends. If you have on a single tracker, you can as well have a PV module on a single tracker. So depending on your configuration. So you have a 2-axis tracker which can track both east to west, north to south, depending on whichever direction the sun is the highest. It follows it in that direction. But again, you must also consider the cost. So we've talked about the PV modules, we'll talk about the inverter, we'll talk about the tracker. Now, assuming that you're not doing battery. Later on, we're going to talk about the sizing of the battery and the inverter as well. I didn't talk about the sizing yet. There is a section for that. So let us look at the physical aspect of a PV system. So I've talked about the cell, the PV cell power output. The electrical power P for now. This is a little bit technical, okay? So I'll urge everyone of us to pay a little more attention to this. So the electric power P for DC system measured in watts is the product of voltage measured in volts and current measured in ampere. This is just when I was in the introduction, when I was talking about the energy and power, I told you to keep in mind this very formula. Sorry, let me just admit people on the waiting room. Okay, so that's good. So power is equals to voltage times current. Voltage is measured in volts, current is measured in amperes. So basically, that's what happened at the PV cells level. If you look at the diagram, you're going to see that the sun is shining on that PV cell, and then it creates the voltage differential, okay, that now allows the current to move from a point of negative to the point of positive. So under normal sunlight condition, the PV cells voltage remains fairly constant. Under normal sunlight condition, the PV cell voltage remains fairly constant. So what this means that the voltage, as long as there's a normal sunlight, the voltage does not play a significant role in the output of the solar PV system. That's what this statement means. However, the cell current is very sensitive to sunlight intensity. High solar irradiance will produce a higher electrical current. Low solar irradiance will produce a low electrical current. So if the intensity of the sun is high, then it follows that you're going to have a higher current. And a higher current will eventually produce a higher power. Now look at it. P is equal to V times I. That is voltage times amperage. At a normal sunlight, this voltage will just almost remain constant, but the current at the higher sunlight this current will increase. So when this current increases and you multiply with the voltage, your power output will automatically increase. If it decreases, you multiply by the voltage, the power output will automatically decrease. So that is the correlation. So that's one of the factors that affects the output of your PV module, the sun intensity. That's one. You can just note that. Then secondly, the surface area of the PV cell also affects the electric current output. So a cell with a large surface area will produce more electric current than a cell with a small surface area. So this is the same thing as saying that the more PV modules you have, the more electricity that you can generate. The less PV module you have, the less electricity you can generate. So those, the two main factors that affect the output of a PV cell are the intensity of the sunlight falling on it and the size of the cell. Okay. Other factors are also important and will be discussed in the following section. So now let us look at electrical characteristics of generating power using a PV modules. Okay, so remember I talked about power. I said you should note this formula. We're going to be making a lot use of this formula. So power is equal to voltage times current. Now let us look at the character, how they behave at the PV level. Okay, so there's a curve that is used to represent what is going on at the PV, at the cell level. There's a curve that is used to represent what is going on. And by the time we are done with this, you'll be able to understand some terminologies. You must have heard about maximum power point tracking, maybe MPPT or an inverter and some other things. By the time we are done, you will understand why those are necessary. So the figure you're looking at, this diagram that you're looking at, describes an important electrical characteristics of a PV cell. At any given time, a PV cell is operating with a specific current and voltage, which lies along its IV curve axis. Now, the IV curve axis is the red curve in the figure. So this red curve now, IV means current and voltage, current voltage curve. Okay, that's what that means. So this line shows the current, that's the current I, which is produced over a range of voltages. Remember that the voltage at the very good sunlight, the voltage hardly changes. So I SC represents the short circuit current. SC means short circuit, then I means current. So ISC represents a short circuit current. That is the value at which the current is at, the value at which the current is at a maximum and the voltage is equal to 0. Now, let us look at this red axis here, okay? Now, the y-axis, this y-axis is representing the current. Now, this x-axis is representing the voltage. So if you move the current to the maximum, which is here, 3, if you move it to this point, what does the voltage becomes? Can somebody unmute and then talk? I just want to make sure that we're following. If the current is here at the maximum, what becomes the voltage?
0.
Exactly. Thank you very much. So once your voltage is 0, now look at this formula here. If you put 0 here and you multiply, even though the current is at maximum, what do you have as P? 0.
0.
Exactly. So that's what this is saying. If you try to maximize your current from the PV module, what that means is that your voltage will become 0. Now let us look at the voltage side of it. Now VOC represents the open circuit voltage. Open circuit meaning that there's no load connected to that PV module. That is the value at which the voltage is at maximum and the current is equal to 0. So now remember that this red line is IV curve, right? I say IV curve. I means current and voltage curve. Now, if you're moving voltage along this axis and you move it now, remember I said that your x-axis is your voltage, right? And your maximum voltage is at this point. So if you move your voltage at this maximum point, what becomes your current? You can unmute your mic and talk.
0.
Okay, so we have a problem here. If you want to maximize your current, your voltage will become 0. If you want to maximize your voltage, your current will become 0. Either way, your power will become 0. So what do? So we need to now look for a point on this red axis where voltage and current, they're not maximum, but at a point where both of them will yield the highest power output. Okay? You don't want current to be 0, you don't want voltage to be 0, but you want them at a point where they will yield the maximum power output. Okay? So that's where we now begin to talk about the power curve. Okay? Now the power curve of a PV cell is shown by the blue line. This line shows the electric power produced over a range of voltages. Under normal operating conditions, the curve grows and contracts along both the current and voltage axis. So now this blue line represents the power. Okay, so at this point, the voltage is maximum, but the current is 0. Okay, or you can say the current is maximum, the voltage is 0. So you have 0 power. But it begins to grow as you begin to adjust both your current and your voltage until you get to a maximum point and it begins to drop, and it drops almost sharply. So the point for us is to locate that point where this power is maximum. If you locate where it is maximum, you drag it down to your IV curve. At that point where you have a maximum power, that is what we call maximum maximum point power tracking. Okay, that's where you have your MPP. Okay, maximum point power. That's why sometimes when you hear about inverter, you begin to hear something about maximum point, MPPT. Okay, so some inverters are not MPPT, meaning that they cannot track, they cannot tell you where the maximum point where you can generate your maximum power. Okay, so the maximum power, which is MPP, the point at which the cell produces the maximum power, occurs at the knee of the power curve, where the product of voltage and current are greatest. The maximum power is thus, that is maximum power, that is MPP, is equal to voltage MPP times current MPP. I hope that's clear. So now let's all look at factors that are affecting power output. Okay. So electrical characteristics and the IV curve. We are still going to make reference to this IV curve that I just explained, because obviously you know that the voltage and current has a way of affecting your power output. Okay. So we'll look more into details how these things happen. Then there are 3 critical factors which affect instantaneous output of a PV cells or module. One of them is the solar irradiance, incidence on the surface. I talked about this, the intensity of the sun falling on the surface of the PV module. Then the second one is temperature of the PV cells. And then the third one, which is not very well pronounced, is the electrical load resistance connected to the PV cell or module. I think I need to mute everyone. I'm hearing some background noise. Can you just mute yourself? If everyone should please mute themselves so I just continue. So I'm going to talk about the first one, the solar irradiance. Now, I'm still going to come back to this IV curve. Okay. Now, the output power of a PV cell or a PV module directly depends on the solar irradiance incident on the surface. As irradiance G increases, the current I increases due to increase in the level of photovoltaic electric effect. I think I've explained this before. The more you have, now all this curve that you're seeing here is actually the current. If you look at this graph, you see that the voltage, which is on the x-axis, does not change much. It doesn't really change much with the intensity of the sun. If you look at this different category of sun here, this is in the morning, it's still cloudy, then the sun is gradually coming out and the sun is fully up in the sky, okay? When the sun is fully up in the sky and when the sun is just coming out in the morning, you find out that the voltage difference is not much. You will notice that because under normal sunlight condition, the voltage rarely change. But the current is what actually changed a lot. Okay, so the amount of sun that is falling on the PV surface has a lot impact on the output of the module. So the voltage output, on the other hand, varies only slightly with changing irradiance. I think I've explained this already. So let me just proceed. So passing cloud or people will cast shadow on the PV modules will cause a drop in current output. Since current is directly proportional to power, shading has a significant effect on the power output. So I think it's important we also note this about shading. Even people, when you have a solar module and people pass and they cast shadow on the module, it is expected that for that moment that people are passing, the output of that module will drop. If you have a tree that is casting shadow on the modules, the performance will drop. So it's very important that we consider shading when we are installing or constructing the solar systems. So let us look at the impact of temperature. Okay, so the performance of a PV cell also varies with temperature. Since PV cells and modules cannot convert 100% of the absorbed light into usable electricity, some of this energy is lost in the form of heat, which causes the temperature of the cell to increase. This is a normal part of the operation of a PV cell and cannot be avoided. As the cell gets hot, the power output drops. This is because the open circuit voltage, that is VOC, open circuit voltage, decreases significantly when the internal cell temperature rises. Now, remember I talked about that the voltage does not really change when, depending on the irradiance of the sun, it does not really change. But here, guess what? Here is what actually affects the voltage: temperature. If there's a slight increase in temperature, it affects your voltage. So look at this graph now. Okay. Now, what we're seeing here is different temperature range. You can see here you have 25 degrees centigrade, right? You have 0. Okay, you have minus 25. I was wondering. You have minus 25 degrees. You have 0. You have 25. You have 50. You have 75. Did you see the degree of change in the voltage because of change in temperature? Whereas when the sun irradiance was increasing, the voltage didn't actually change much. But here, we are not talking about the temperature. Remember that when the sun falls on the solar panel, all the sunlight that hits that solar panel is not converted to electricity. Some of them are converted to heat, and it heats up the solar module. And once it heats up the solar module, the temperature begins to rise. And once the temperature begins to rise, your voltage begins to drop. And once your voltage begins to drop, automatically your power output from that PV module will drop. Remember that power output is voltage times current. So either a drop in current or a drop in voltage will reduce your power output. This might sound somehow because you need sunlight to generate this power. And now I'm telling you that when the temperature increases, it affects the performance of the solar PV. And that's why in the very hot weather, solar PVs might not perform well. They might not perform at optimally, in as much as you have a very good sunshine. If the heat within those regions is high, the solar PV will not perform optimally. So we need to take this into account. So under normal condition, the PV cell will always operate at a temperature higher than the ambient temperature. So what this is saying that if the ambient temperature is, for example, 45, okay, of course you should expect that the temperature at the surface of the PV should be greater than 45. Now this is just a rule of thumb. Okay, so the ideal operating state for maximizing power output is high irradiance with low temperature. So you want that irradiance to be high, but you don't want to increase the temperature. So those situations those kind of weather are the best weather for solar PV systems. So such conditions are rare. Example, I mean, now where you can find such kind of weather it's high up in the mountains in winter, that's in winter on a clear day, high up in the mountains in the winter days. So that's where you can find this kind of conditions. Somewhere around far in the northern part of Nigeria, of course, you have very good sunlight. I mean, high irradiance, but of course, the bad news is that you also have high temperature. So that's high temperature also affects the performance of PV modules in those regions. So we've talked about irradiance, we've talked about high temperature now. And these are the things that affect the outputs of a PV module. Now let us look at impact of load resistance. I think the load resistance here has a lot to do with Ohm's law. So an electrical load connected to a PV module will determine the point on the PV module IV curve where the module will operate. An electrical load could be light bulb, a pump, a grid, or a battery. If there is less sunlight available, then the load will pull less current, definitely. So the voltage across the load and the amount of current that the load pulls from the module is determined for a given irradiance and therefore for a given IV curve by the equation. So now this is Ohm's law anyway. Current is equal to voltage over resistance. Current is equal to voltage over resistance, where I is the current in ampere, voltage is the voltage, I mean V is the voltage in volt, and R is the resistance in ohm. So what this simply tells us that, look, if you have a higher resistance, okay, if you have a higher resistance, it affects the current that will automatically be produced from your solar PV system. And the resistance has to deal with the load, okay? If you look at this equation, you see that current is inversely proportional to resistance. So higher resistance will reduce the current. And this is the same current that is coming from your PV system. So there's a note here about batteries. Now, if batteries are connected to the PV modules, as in an off-grid system, the battery will determine the voltage at which the PV modules operate. The module output current will then correspond to the module IV curve at that point, at that voltage. Like I said earlier, this is less pronounced in terms of the impact of load resistance on the performance of PV modules. But it is important that you know that somehow the load that is connected to a PV module has a role to play in the performance of the PV module. That's what I just wanted to, the knowledge I wanted to share with by this. So now there's what called standard test condition, STC. Before I proceed, I think I'm thinking if we can take a 10 minutes break. Okay, then we'll come back. What's the time now? This is 4:31. Can we just take a 9 minutes break and then come back by 4:40? I need the house to respond. Please.
Let's continue, sir.
Let's continue. Okay. I just don't want to decide on just one opinion. Do you have other people who want us to continue, or you want us to take a 10 minutes break?
Please, let's take the break. Please, let's take the 10 minutes.
Trace-wise, I will advise you take a break, please.
Okay.
Let's
Okay.
take
a break. Huh?
Okay, please. So let us please take a. Now our time is just 8 minutes break. Yeah, 8 minutes. So by 4:40, please let us come back. Okay.
Okay.
All right. Okay. So your break starts now. Engineer Ushe. Okay, I think he's not here. Otherwise, I will just continue. Sorry, because of my focus on the training, I'm not able to read all the messages in the chat box.
Okay, a quick one. I think Tosin asks, is sunlight the only source of radiations to the PV cells?
Okay. No, not really. Any source of light. well, it depends on the kind of light anyway, because there are some, now light is an electromagnetic wave, but a visible form of electromagnetic wave, right? So if you have any source of light that meets the characteristics of the natural sunlight, will automatically work. So to answer you, I mean, it's not only sunlight. Okay, so I take it that that is well understood. So I proceed. Can every other person please mute themselves? I'm still waiting for those of you that have your mic on to please unmute yourself. Okay, I'm just trying to do the unmute myself. So fine, let's proceed. Before the break, I was going to talk about the standard test condition. So due to the variability of power output of PV cells, depending on parameters such as irradiation and temperature, the performance of different cells operating under different conditions cannot be compared easily. Now, remember there are characteristics, factors that affect the output from these PV cells, PV system. So, because these characteristics are not uniform across the globe, okay, so we need a standard parameters to say, okay, this is the performance of these PV cells, so that if it deviates from that performance, we can then attribute it to the deviation of those parameters in your location, okay? And that is the whole essence of having what we call the standard test condition. So it enables us to be able to determine how the factors in your locality has affected the performance of the solar module, okay? So you need a baseline to compare. So in order to enable meaningful comparison between PV cells or PV modules, the rated output of a cell or a module, the rated output of a cell or a module is always measured under specific conditions. These conditions are standardized across all testing facilities worldwide and are called standard test conditions. So what are the standard test conditions? One of them is light spectrum, okay? The light spectrum is AM, and AM is I think air to mass ratio is 1.5. Then you have irradiance, is 1000 watts per meter square, okay? Then you have cell temperature. Remember, these are the irradiance, the temperature on the surface of the panel, okay? These are the major factors that affect the output of a PV module. So now these are the standard conditions that any PV module that you found in the market, these are standard conditions that they have been tested to be rated. So if you see a PV module that is rated 300 watts, 300 watts is based on the condition that it has been tested with irradiance of 1000 watts per meter square, and it has also been subjected to a temperature of 25 degrees centigrade and a light spectrum of 1.5. So each finished PV cell or PV module leaving the production line undergoes a flash test. It is exposed to a flash of light under careful control of the STC parameter, standard test condition parameter, lasting only milliseconds, and the output performance is recorded. Subsequently, the cell or module are sorted and sold according to their rated power. The rated power is measured in units of watt peak or kilowatt peak and refers to the rated power under standard test conditions. So when you see all those ratings of PV modules, okay, you say 300 watts, 250 watts, 200 watts, or whatever the case may be. Okay, it's actually the performance under this condition. So it's not, there's no guarantee that when you put them in your location, they're going to do 300 watts. Okay. So, but however, if you provide them with this condition, if you subject them to 25 degrees centigrade, 1000 watts per meter square, and then light spectrum of 1.5, it is expected that you're going to get that rated output. But however, this case is not always it's not always the same. So let us look at temperature coefficients. Remember I said that temperature affects the voltage of your system, and once the voltage is affected, your power output is also affected. So to what extent does this temperature affect your PV performance? So we use what we call temperature coefficient to determine that, okay? So the temperature coefficient shows how voltage, current, or power output of a PV cell or a module change with changing temperature. Now, the module data sheet gives temperature coefficient. When you get your module sum, it is expected that you see the temperature coefficient inscribed on it. Now, for an open circuit voltage under standard test condition and under short circuit current condition as well, meeting the requirement of the standard test condition, which is 25 and the 1000 watt per meter square. And power at the maximum point is also provided. Now, these are the part of the details that you should expect to see from the PV module datasheets. Now, the details that you are seeing are the performance of that module under standard test condition. So the voltage temperature coefficient is the most common one used. Inverters and other devices such as charge controllers can be damaged by modules or strange voltage that exceed the specified input voltage. And these inverters and other devices, I mean, if you exceed the required input voltage for your charge controller or your inverter, of course, you're most likely going to damage those electronic equipment. So that's why it's important that you look at your VOC, your open circuit voltage of your solar modules. Now, depending on your desired voltage, the desired voltage that you need to feed into your charge controller or your inverter, okay? You can then place your PV modules. If you place your PV modules in series, you increase the voltage. I said that again. If you place your PV modules in series, you increase the voltage. So you can keep placing them in series until you get the required number of voltage that you need to feed into your inverter or your charge controller. However, you can as well place them in parallel. But if you place them in parallel, you're increasing the current, not the voltage. So the voltage remains the same. So if you put your PV in series and you get the required number of voltage, you can then put the rest of the panels in parallel to increase the current. The voltage will then remain constant. Unfortunately, I didn't have a pictorial representation of what I just explained, but I hope that we'll be able to understand that. So voltage temperature coefficient. Voltage temperature coefficient is given in the form of example minus 0.156 volts per degree centigrade, or minus 156 millivolts per degree centigrade, or as a percentage per degree centigrade. So what this simply means is, for every rise in temperature, for every unit rise in temperature, your voltage drops by this. That's what it means. Okay, that's what this voltage temperature coefficient tells us. For every rise in temperature, if your temperature rises from 25 to 26, then the voltage of your VOC at standard test condition would drop by 0.156 volts. Okay, so that's what it means. Or you can also express that in percentage. So now the same thing also happens for current. But in current, when I was talking about temperature, effect of temperature, I did not talk much on current, because temperature does not affect current so much. If there's a rise in temperature, in fact, in actual sense, it increases your current, but not so much to compensate the losses that your voltage is bringing in. Okay, so that's why we don't dwell so much on temperature effect on current. So current temperature coefficients are given in the form of, you can see that the numbers are very low, 0.0029 ampere per degree rising. So for every degree rise in temperature, your current can increase by this above the standard test condition, right? Now, but you can imagine for that degree rise in temperature, your voltage will drop by 0.156 compared to 0.0029 ampere. Okay, so the drop in voltage is so significant that this gain is irrelevant. Okay, so that's why it is important. So that if we're going to do some mathematical example, so that if you want to install a solar PV in a node and you measure the temperature, and the temperature, for example, is 36, okay? But of course, you know the standard test condition is 25. So you know the difference. For every degree rise in temperature, your voltage is going to be. So it helps you to calculate the amount of losses you're going to have because of that high temperature. That's what this helps us to achieve. Then you also have the power temperature coefficient. Of course, you know that if your temperature affects your current and your voltage, automatically your power will be affected based on the relationship of power is equal to voltage times current. So now you can see the impact of what I've just explained now. For every rise in temperature, your power does not become positive. It's negative because your voltage depreciates so much that the increase in your current is not enough to make it positive. So for every rise in temperature, you lose the power output of your PV module by minus 0.42. So that's what the power temperature coefficient tells us. You can as well express that in percentage. So this is a little calculation exercise. So assume the following data. The yearly daytime temperature of a location ranges from -10. Now, apparently this is not for Nigeria. So -10 to plus 45 degrees centigrade. So a PV module is being installed, which has the following. An open circuit voltage, that is VOC, of 43.24 volts at standard test condition. So when the voltage is this, your current is 0. That's what it means, okay? And then there's no power output. But again, it has a maximum power point of 35.35, meaning that this is the maximum, this is a point where you have the maximum power output, okay? And that is at standard test condition. At this VOC, your current is 0 and your power output is 0. But your VMPP, maximum power point, is lower than this, so it's 35. So a temperature coefficient TC at the VOC is minus 0.168636 volt per degree centigrade. Now note that temperature coefficient at the temperature coefficient TC at the maximum power point is slightly different from the temperature coefficient at the open circuit voltage. Okay. Now this is the case for. Now, sorry. In the case of this calculation, the difference is neglected. I try to explain that. The temperature coefficient at this voltage will be different from the temperature coefficient at this voltage, but is a slight margin. So for the purpose of this calculation, we're going to neglect it. So we are going to assume that this temperature coefficient at open circuit voltage, that's for every degree rise in temperature, you lose this voltage, is also applicable both at the maximum power point. That's what I'm trying to explain here. So this means that for every degree centigrade temperature drop below 25 degrees, the module voltage will rise. If your temperature drop, then your voltage will increase. Similarly, for every degree temperature rise above 25 degrees, the module voltage would drop by this. Okay. So let us look at the calculation now. So what will be the maximum voltage produced by the module? Maximum voltage that is produced. Now the maximum voltage is at an open circuit voltage, not at the maximum power point. So what is the maximum voltage when the current is 0. That's what it means. Anytime you see VOC, it means that the current is actually 0. So the maximum open cycle voltage will be produced at the lowest ambient temperature. Remember, I said that with every degree rise in temperature, your voltage drops. But every degree drop in temperature, your voltage increases. Okay? So at the lowest temperature, at the lowest ambient temperature, which is -10, that's where you are going to have the highest open circuit voltage. So the lowest cell temperature would be -10. Remember in our, trying to go back. Remember, you might just want to write some of these things down, or if you have printed the material, you can always look through the data that we are given. Okay. So I was trying to make reference to the temperature range that we were given. We are given a temperature range of -10 and +45. Okay. So you have your greatest voltage at -10 and your worst voltage at 45. And this question is asking you for the maximum voltage. So you're going to have your maximum voltage at -10. So now your VOC, which is -10, is this, your voltage at -10 is equals to the VOC voltage that you are given, okay, plus 25 degrees centigrade minus -10 times your temperature coefficient for voltage. When you do this computation, okay, you're going to get 49.14. Now, this is your open circuit voltage, the highest voltage you can get. And at this voltage, your current is 0. So what will be the maximum voltage? That's voltage when the module is operating at its maximum power point. That is in full sun produced by the module. Now, this is not acting at this point. Now, you're not looking at VOC. Now, you're looking at VMPP. Okay, so at this time, this is when the panel is operating maximally at the maximum point. So they're not asking what voltage will it be operating. So at that same point, we are giving the VMPP to be 35.35, which is lower than the VOC. I hope you're catching up with the way I'm mentioning these terminologies. However, if you have the materials, by the time you go through it over and over again, you become very familiar with all of this. So when you now deduct the lowest temperature from the standard test condition temperature, which is 25, and you multiply by the temperature coefficient, you're going to have 41.25. This 41.25 is lower than the VOC. Okay. Remember, at this VOC, your power output will be 0. But you want a power output to be maximum, so your voltage will reduce to a point where your current will be maximum as well. So you have 41.25 volts at that point. So what will be the minimum voltage? Now, the minimum of this will now be the opposite of what we have done here. Okay, we use -10. So in this case, you're going to use -45, not -45. We're going to use 45 degrees centigrade. So what will be the minimum voltage produced by the module? The minimum voltage will be produced at the highest ambient temperature, which is 45, but the cell temperature of the rooftop or open field PV system can be 25 degrees centigrade higher than the ambient temperature. I said this earlier when I was talking about the impact of temperature on the solar panel. When the sun shines on the solar panel, not all the sun is converted to electricity. Some of them is used to heat up that panel, and the panel becomes hotter than the ambient temperature. Okay, so if the ambient temperature is 45, you expect that the temperature at the surface of that panel would be higher than 45. So we are assuming that it is 25 degrees centigrade higher. So if you add 25 to that 45, you have 70. That's what I'm trying to explain here. Okay, so the temperature at the surface of that PV module will be 70 if the ambient temperature is 45. So we are working with 70, not 45. So the open circuit voltage at 70 degrees centigrade would be your open circuit voltage that was given plus 25 minus 70. Of course, when you do this minus, it's going to give you a negative value. When you multiply it by this, you will get 35. Now this is the minimum voltage at you can get when there's no load connected on the PV module and the current is 0. And this is the maximum, 49. The minimum is 35. Now let us calculate the minimum voltage at the maximum power point. So when we do that, we also use 70 degrees centigrade. Okay, but in this case, we are using the voltage at the MPP, which was given to us at 35.35. So when you do that, you're going to get the voltage of 27.76 volts. This might look a little bit confusing, but I can guarantee you that by the time you take your time to study it, it's very simple. It's a very simple mathematics. So let us move ahead. Orientation and inclination of PV modules. How do you orientate your PV models to capture the maximum power output? And at what angle of inclination do you position it? So the PV module's orientation and inclination or tilt angle significantly affect the amount of irradiation that the surface receives, and hence the amount of energy that the modules produces. In the northern hemisphere, the PV module should be facing south, whereas in the southern hemisphere, it should be facing north. This guarantees the maximum irradiation level on the PV modules throughout the year. In regions close to the equator, the orientation is less important. I will explain this. The optimum tilt angle of a PV module depends strongly on the location. Okay, as a rule of thumb, the module should be tilted to an angle equal to the latitude of the installation site. So if you want to install a PV module, here you will see that they were talking about how do you face it. Where do you orientate? Do you face it to the north? Do you face it to the south? Do you face it to the east? Do you face it to the west? The most important thing when you go on a site to install a PV system is to locate your axis. Where is the north? Where is the south? Where is the east? Where is the west? And then you know that the sun rises from the east and sets in the west. Okay. Now, in which, if having that in mind, the next thing you're going to ask yourself is that the location where you are, is it toward the north of the equator or toward the south of the equator? If you're on the north of the equator, there's a figure. Okay, let me illustrate that with this figure. So now, that you're seeing is assumed to be the equator. Okay, so now here is the north of the equator. Here is the south of the equator. So if you're located in this northern part of the equator, your PV should be facing south. That's what that is. Now, Nigeria is located somewhere here. Nigeria is located on the northern part of the equator. Nigeria is located somewhere here, about between 4 to 13 or 12 degrees centigrade. That is the latitude. If you're in the south, Bayelsa River, it's about 4, 5, but as you move towards the north, the latitude begins to increase to about 12 or 14 thereabouts. So if you're installing a solar PV in Nigeria, this rule of thumb, let me point it out. Now, a rule of thumb should be that the module should be tilted to an angle to the latitude of the installation site. So what is the latitude of the installation site? If you determine the latitude of that installation site, I even stated here that Nigeria is situated in the northern latitude between 4 degrees to 14 degrees. So if you're starting a solar PV in Nigeria and you're doing above 20 degrees, I mean, I don't understand what you're doing. I mean, that's how to be professional about this. So you need to look at the latitude of your location. Two things are very important. One of them is the latitude. Then the next one is your hemisphere. Are you on the northern hemisphere or you're in the southern hemisphere? So if you're in the northern hemisphere, your solar PV should face south. And like I said, Nigeria is somewhere here. We are in the northern hemisphere. If you're somewhere here, it only looks stupid for you to place your solar panel to the south because the sun is already coming from somewhere here. So you have to face it to the north. So those are the terminologies. So if you look at this sun track here, you see that this is for summer. This one where you have the pure yellow line is for summer sun. And then this is for spring and autumn, and this is for winter. Now, these seasons are not clearly distinct in Nigeria, okay? So I just use this image to illustrate what this slide is talking about. Now, the roof-mounted modules are usually simply installed at the same angle as the roof. Since the extra cost of adjusting the tilt angle exceeds the benefit of the extra energy that will be generated. Now, what is saying that just because I've said that, oh, you shouldn't do more than 20%, I mean 20 degrees in Nigeria, ideally maybe 15 degrees is fine, okay? And you now see a rooftop that has 35-degree angle inclination. You not take the owner of the house that no, you have to re-roof your house and they do it 15 or 20, okay? Or you have to now begin to bring in some mechanical structures so that you can get that tilt angle of 15. If you look at the cost of doing all of that, then it outweighs the cost of doing all of that, outweighs the benefit, the extra energy that you will get. So that's what this is simply saying. So if you're placing a solar panel on a roof, it simply says that because the roof is already there, you just use the angle of the roof to install your panel, the tilt angle of the roof to install your panel. Since the cost of trying to change the roof angle, it outweighs the benefit of the extra energy that you're going to generate. So in regions close to the equator, the most solar irradiation is captured if the PV module is flat. Now, if you're almost on the equator, let me go back there. So if you're on this equator, if you're almost on the equator here, I mean, you're just so you can just put your solar panel flat. That's what it's talking about, okay? So in regions close to the equator, the most solar irradiation is captured if the PV module is flat. However, in practice, a minimum tilt angle of 10 to 15% is recommended to allow for self-cleaning. If you put it flat, I mean, it's going to get dusty, quickly enough and begin to affect the performance of the module. So it's advisable that at least you have a tilt angle of 10 to 15 degrees so that at least some other particles can follow the surface of the panel. So this is about the orientation and then the angle, the tilt angle of your solar panel. So one important tool to use here is your compass. You use your compass to determine the hemisphere, the latitude of the location where you're having that installation. Someone raised his hand. Okay, can you unmute yourself and speak, please?
Okay, yes, I need to ask a quick question here.
Okay.
With regards to the orientation and inclination of tilt of the PV modules.
Okay.
Let us say I live in Port Harcourt.
Okay.
That's in River State.
Okay.
And I don't have a compass. I'm just giving you a hypothetical example. I don't have a compass.
Okay.
Is it wise for me to just use, since the house is already built and the tilt is already in place, can I just place my solar panels on the roof as is if I don't have a compass?
So when you look at the roofing of the house, I'm also assuming that the roofing of the house should have different orientations. You know, it should have some part of it maybe facing to the east, to the south, to the west, or to the north. But then, as a professional, it is always necessary that you be able to locate where your south is, because it looks unprofessional for you, in as much as you don't want to begin to re-roof the house, but you want to be able to locate that solar panel at a point where it can capture the maximum amount of power, depending. I mean, although there's a limitation of the roofing of the house, but again, you don't want to make that mistake of choosing the worst location on the roof, right? So it is highly recommended that you be able to identify. I mean, there many phones these days has compass. I mean, you can just install compass on your phone, depending on the kind of phone that you have. Okay, a lot of Android phone now you can download and install compass on them. So it's not a sophisticated tool for you to have, okay? Just for you to know where the south is, okay, so that you'll be able to achieve the maximum output from the solar panel. I don't know
Okay,
if
I think, yes, I understand that. I was just asking. Now, the
Okay.
other quick question is, Port Harcourt is already in the south, correct?
Yes.
Okay, now if I locate through the compass where my south is, all I have to do is just to orientate my panel to the opposite direction, which is the north, correct?
No, not correct. Now, when I talk about the northern hemisphere, it is
Yes.
actually different from the north, south, east, and west of Nigeria.
Nigeria.
North, south, east, and west of Nigeria, it's also identified through the compass, right? But for the fact that you're already in the south or southern part of Nigeria, now look at, this is the equator, this is Nigeria somewhere here, and the south that you're talking about is also still here.
Right.
You understand? So you're still in the north, despite the fact that in Nigeria you think you're in the south, but you're in the southern part of Nigeria, but on the equator you are still in the north.
North.
I don't know if you understand that. This is Nigeria. This is where Nigeria is, somewhere here. Okay. Maybe the north will be here and the south will be here. Okay.
Okay.
So despite the fact that you think you're in the southern part of Nigeria, which is somewhere here, you're still in the northern part of the equator.
Okay.
So your orientation still has to face to the south.
Okay, which is the other end,
Yes.
this other end.
This
here.
other end, yeah, this other end, yes, exactly.
Okay.
If Nigeria were to be somewhere here, okay, then that is only way you can now. If Nigeria were to be here, whether you're in the north or you're in the south, your orientation must face to the north.
North.
Yes. If Nigeria were to be here, you're seeing my cursor, right?
Yes.
So if Nigeria were to be somewhere here, whether you're in the southern part of Nigeria or in the northern part of Nigeria, your orientation must face to the north. But Nigeria is just somewhere around here. Nigeria is between, I showed you now, between 4 to 14 degrees north of the equator.
Okay.
So yeah, so that is it. Thank you. Thank you for the question. So I have already explained this with this slide. So now let us look at the solar yield estimation. Now, why it's very important that I have to take you through all of this. And sometimes I see some of you talking about software and all of that. It's also important that you know what this software does. Okay. Sometimes because people are not very professional, they just use software to do some of this. So you just go to the software. The software will ask you, which country are you? You tell the software that you're in Nigeria. What that software actually does, the software already know that Nigeria is in the northern hemisphere. It can ask you which state are you. You tell him you're in Port Harcourt, you're in River State. The software already know the latitude of River State. So it's just going to tell you, okay, this is your teeth angle. It will equate your teeth angle to the latitude of the north of your location. So the software is not doing magic. You need to understand some of this so that in the absence of the software, you can still be able to do your design and produce some results. That's why it is important you know some of these things. Okay, now we are talking about solar yield estimation. Sometimes you put some of these details on a software and it tells you this is the amount of solar energy you're going to get. It's not magic. There's a way the software was able to determine and calculate all of this. Okay, this is very important. That's why important we're having this training. So you understand some of this so that in the absence of the software, you might find yourself in a group of people who are doing design. Just last month, I designed a mini grid I was in Cross River. I went to do an energy audit for a community, and I came back. I worked with a team to design that mini grid. Okay, and we didn't use any software. We did that mini grid, and we submitted what we needed to submit, and everything was successful. Right. So sometimes some of this software, they're not perfect at work. Sometimes they can also malfunction. So how do you know when they malfunction? So it's good you understand all of this terminology and how they are being worked out. And that's why it's important we're having this training. Okay. So let us look at solar yield estimation. Now, this is a map of Nigeria. Okay, so in order to assess the energy yield of a solar PV system, one has to know about the available resource inputs to the PV system, meaning the solar irradiation. Okay, what the solar PV system needs to work is the sun. Okay, so when you look at this map, okay, you find out that you have more of the sun, you know, at this region, but unfortunately, I think you have a higher temperature as well at this region. So you have to calculate the effect of this temperature on your installation, you know, and then know if it's most viable to the project. I need to mute someone, otherwise you just mute yourself. Okay, I think the person has muted. Okay, so the color-coded solar resource map provides a first indication of the available solar energy production potential in a certain region. Now, this is what most of this software uses. If you tell them you're in the north or the region you are, so they already know what the solar radiation of that region is like. So they can be able to say, okay, this is an estimate of the amount of energy that you can actually get if you put certain number of size of solar system. Okay. Okay. So the input data are usually provided as an average annual sum in kilowatt hour per meter square. Okay, so for every meter square, how much energy can you actually get from the sun that is available at that location? So the darker the color, the better the resource potential. So the economic feasibility of a PV plant critically depends on its electricity yield. The whole essence of you doing a PV system is the electricity that you're going to get out of it. That's the hallmark of what you're doing. So you must be able to identify everything that will negatively affect the output of that energy, and then find a way to deal with them. Okay. So the electricity output of those solar panels, which in turn depend on both the meteorological condition at the location and the performance of the plant itself, the weather condition of the area, and of course, the performance of the plant, the kind of inverter, the kind of PV modules you're using, and all of that, and as well as your design, how you design the system. So as the electricity yield is heavily dependent on solar irradiation level, it is essential that accurate and long-term climate data are available for the given location. Solar irradiation at a site is often stated in terms of peak sun hour over a certain period. Now, in the next slide, we'll explain what this peak sun hour is, okay? So furthermore, component quality, I think I said this, the quality of your inverter and all that thing. So the component quality, plant design and layout, as well as the maintenance plan will affect the performance and consequently the energy yield of the plant. So let us talk about performance ratio. We'll definitely talk about the peak sun hour, but I'm just introducing it here. We'll talk about it in the later slide. So let us talk about performance ratio. So we want to look at the performance of solar PV systems. What are the things that actually affects its energy yield, right? So performance ratio is one of the factors. So what is performance ratio? The performance ratio is one of the most important parameters for assessing the performance of a PV plant. It is the ratio of the actual plant output to nominal plant output at STC, standard test condition. So you have a PV module, it's rated 300 kilowatt peak. No, sorry, 300 watts peak, right? It does not mean that when you deploy that solar PV, you're going to get 300 watt peak, unless you provided the same condition at standard test condition. But as long as your conditions are not the same with the standard test condition, it's going to vary. And this variation is what we know as performance ratio. So in actual sense, the formula for the performance ratio is the actual output, that is the actual energy that you get from that solar PV that is rated 300 watts peak, all over the 300, that is the theoretical output. Now that solar module has been designed and labeled 300 watt peak that's going to give you the 300 watt peak. So the actual energy that you get from that PV divided by that 300 watts is what gives you the performance ratio. So when you do that, you're going to get something less than 100%. Okay, so that's what performance ratio is all about. So it is determined by monitoring the actual plant output over a defined period, easy maybe for 1 year, and dividing this by the nominal plant output in that same period. I think this is clear enough. So the performance ratio will change from period to period, depending on environmental and technical conditions at the plant. Of course, environmental conditions change. The temperature will not remain the same. The temperature at Hamatan is different from temperature at rainy season. So the idea is that when you monitor that plant for 1 year, you cannot take the average performance and then you now compare it with the theoretical output of that plant. Then you can be able to determine your performance ratio. Now, a low performance ratio is indicative of how to produce 300 watts and you're getting maybe 200, okay? Which means you're losing. So that's what it simply means. So the higher your performance, the lower your performance ratio means that you're losing more energy that you ought to have gotten. So for example, due to high module temperature, reflection of solar irradiation from the module, soiling of the front glass, shading, component failure, mismatched module output, etc. Therefore, the higher performance ratio values, sorry, I didn't get it. So therefore, higher performance ratio values are desirable. I just explained this. You desire a higher performance ratio for you to be able to actually get the value for your project. So in contrast, performance ratio is also used with common reference value in the planning stage of a PV. So just to help you during your design stage, if you're designing a solar PV system, theoretically, you can assume certain performance ratio because you can't just take 100% performance ratio. It is not ideal, it's not possible. So it also helps us when we are doing our design to estimate certain losses that we expect from the system. So for example, a PR of 0.75 to 0.8 is used for grid connected PV plant. If you're designing a PV connected grid connected PV plant, you can use 0.75 to 80, meaning that if the solar panel can give you 100 units of energy, 20 is going to get lost, or 25. Okay, you're only going to get 75 or 80. That's what it means. Okay. Then, but if you're doing for an off-grid plant, you can just use like 65, 0.65 or 65%. If you're doing for an off-grid PV, so it helps you to be able to, estimate the expected losses from your design system, from your design. So this means that the expected gross energy production potential would have to be multiplied by the performance ratio value or reduced by 1 minus performance ratio to reflect the expected production after system losses. I think I've explained it. Once the energy yield of a PV system has been estimated, then the revenue from the electricity sale can be calculated in order to evaluate the profitability of the project. Okay, so you cannot just design with 100% performance rate. If you do that, then it's unprofessional. It cannot be realistic because you're expecting that the solar panel is going to produce 100 units of electricity, and you're going to sell that 100 units of electricity at a certain price, and you're going to realize certain revenue. That's your design. By the time you now implement that project, you find out that what you've designed is not realistic. So it's very, very important that while we are doing our design, we try as much as possible to be realistic. And that's why it's important that we use some of this terminology. We know what performance ratio we are going to use in our design system. So energy yield calculation example. Now the following equations provide a quick and simple way to estimate the energy yield of a PV plant over a particular period of time. So energy yield is equal to peak sun hour. Now the peak sun hour is coming here. Remember I had introduced it earlier. So the peak sun hour times the peak power output from the solar PV model, then times your performance ratio. So if you know what your peak sun hour is, and you multiply it by your rated output of your solar PV model, maybe 300 watt peak, you times it by that, then you times it by your performance ratio. If you're designing for a grid connected system, you can use 0.8. If you're designing for off grid, you can use 0.65. 65. So when you do that, you actually get your energy yield. So this is just a definition of what those times are. So the peak sun hour is an imaginary case where the sun shines at a constant irradiance of 1000 watts per meter square for 1 hour. That's what a peak sun hour is. I think I'll explain it in the next slide. So we can visualize the peak sun hour by looking at the area below the solar irradiance curve. This area must be similar to the area of a rectangle with a height of 1000 watts per meter square. The width of the rectangle determines the peak sun hour. Now look at what it is. During the morning time, and now this is the morning time, 8 a.m., and the sun comes out, okay? It begins to increase. I mean, the irradiance of the sun begins to increase until it gets to the maximum, which is occurred at about 12 noon, okay? And it begins to drop, okay? Now, for us to be able to calculate the number of hours that we will need to get the energy in this shaded portion, okay? We now have to now assume that, imagine that the sun is out and the irradiance is 1000 watts, 1000 watts per meter square. Imagine it is 1000 watts per meter square. How many hours of sun are you going to get the same amount of energy under this shade? That's what peak sun hour is, okay? Assuming that the sun is at constant, so it comes out and it's at constant, okay? So to enable us to do that, now the reason why we do peak sun hour is just for an ease of calculation, for you to say, okay, so maybe for example in Europe, you can easily find what their peak sun hour is, which should be in the range of maybe about 4 or 5 hours, okay? So every region has this peak sun hour. So it's left for you to just do a little research and you find out what the peak sun hour is, then you can use to do your solar yield estimation, okay? So let us take an example and it becomes clear. Now, looking at this graph, the area under this place now must be equal to the area of this place. However, this shape is irregular, but this one is just rectangular. Does someone want to ask a question? I'm hearing a background noise. Otherwise, kindly mute yourself. Okay. I've done that. So let us take an example. Take here. Bamigwade, do you have a question? I think I just unmuted you then, and then I think I just muted you, then you unmuted yourself again. Do you have a question? Okay.
Chima, just continue, please. Just mute everybody.
Yeah, I've done that.
They can chat up. They can chat up.
Okay. So I was trying to cite an example here. If irradiance of 1 kilowatt hour per meter square, 1 kilowatt hour per meter square is the same thing as 1000 watts. I hope we all know that. So how many sun hour is required to produce 4 kilowatt hour? So we want to calculate the sun hour, which is the same as the peak sun hour that is required to produce 4 kilowatt hour. Okay, so just know that this formula is very important. So in this example that we are given now, we already know what the solar yield is. In this case, we told us it's 4 kilowatt hour. We don't know what the peak sun hour is. Okay, and we know what the peak peak power output, the peak power output is, which is 1 kilowatt per meter square. Okay, we don't know what the performance ratio is, but let us ignore that. So if we make peak sun hour the subject of the formula here, so what that means, we are going to divide the energy yield by the peak sun hour here. Since we don't know what the performance ratio is, let us ignore that. Okay, so if you make peak sun hour the subject of the formula, what you're going to have is the energy yield, which is 4 kilowatt hour per meter square, divided by 1 kilowatt per meter square. So when you cancel out, what you're going to have is 4 hours. Meter square will cancel out meter square, kilowatt will cancel kilowatt. You have only 4 hours. So you have 4 hours. Assuming losses are neglected, because if we know what the performance ratio is, We are also going to divide it by the performance ratio, but we don't know what the performance ratio is, so we know that. So that's why I said that assume that losses are neglected. Okay. So if we do that, we're going to have 4 hours, and which is what we have here. So we're going to assume that the sun comes out and immediately is 1,000 watts per meter square. So that sun will remain at 1,000 watts per meter square for 4 hours for us to get the same amount of energy that we'll get in this chart. So that's what peak sun hour is. That's what it tells us. It helps us to regularize this shape into this shape. If anyone has a question, please do ask. Otherwise, I want to assume that we are all following along. So let us look at more examples. A PV plant developer is planning 2 PV plants, one in Northern Europe and the other in Southern USA, and wants to estimate the energy yield of each to be able to gauge their economic feasibility. So there are 2 PV plants here, one in the Northern Europe and another one in the Southern USA. So he wants to estimate what their energy. So this is the system characteristics for the system in the Northern Europe. It has a rated power of 1,000 watts peak. And we know what the peak sun hour is. The peak sun hour is 1,200. Now, this is annual peak sun hour. This is the total hours of sunshine in a year. And we know what the performance ratio is. So this developer wants to determine the energy yield, the amount of energy that he will get from this system. So the energy yield in Europe will now become the peak sun hour, which we know as 1,200 hours, times the peak of the rated performance of that solar module, which is 1,000 watts, and the performance ratio, which is 0.8. So when we do that computation, we are going to get 960 kilowatt hour per annum. So this is the amount of energy that you can get in a whole year from that system. If you increase this performance ratio to 90, this energy yield will also increase. If you reduce this performance ratio to 70, this energy yield will reduce. Okay. So if you want to know how much you can get from this project in a year, you just have to multiply this energy, this quantity of energy, by the amount that you buy a unit of energy in Europe. So if you buy a unit of energy for maybe 10 euro cents, then you multiply it by this quantity. You get the amount of money you can get by installing this size of PV system in Northern Europe. So let us look at what we get in the Southern USA. So if you do the same project of the same rated power output, 1,000 watt peak, 1,000 watt peak, but in Southern USA, you have a higher sun hour, peak sun hour. So you have a more sunshine in Southern USA. So for a whole year, you have 1,900 peak, 1,900 sun hour. But again, the performance ratio is low, maybe because of temperature. So your performance ratio is 0.7. So let us calculate the energy yield for Southern USA. We'll do the same thing that we did above. You have 1,900 hours times 1,000 watt peak times 0.7. When you do that conversion, you're going to get 1,330 kilowatt hour per annum. So what this means that although the system in the Southern USA has a lower estimated performance ratio due to the higher ambient temperature, the output is higher because more solar irradiation is available. So you can see that because you have more solar irradiation in Southern USA, you have more energy output. So the project in Southern USA is more viable than doing that project in Southern Europe. So once the PV plants are operational, the actual plant output can be monitored, and thus the actual performance ratio can be calculated. Now, this is theoretical. This is at the design stage. Okay, but it's always good that at your design stage, you try to be realistic as possible. So it is expected that when the performance of this plant is monitored over a year, the reality should not differ so much from what you have calculated. And that's how you know someone who has done a good job in their design stage. That is not to say that things cannot go wrong during the construction and operation, okay? But if all things being equal, This is how you'll be able to identify someone who has done a good job at the design stage. So let us look at the load profile. Now we've talked so much about the solar panel, their performance ratio, the energy yield, the peak sun hours, and all of that. Let us not. Okay. Someone, you have a question?
Yes, I have a question.
Okay.
I actually have a preview to some design where they use something, some terminology like panel generation factor and energy loss in the system. They apply that factor in the whole yield for that panel. So is there anywhere we can liken that generation factor, panel generation factor or energy loss in the system factor in what you have demonstrated?
Now, what you're saying, you said panel generation factor, right?
Yes.
Okay, and you talked about energy.
They said it's different from country like in Thailand.
I know.
Yeah.
What's the other one you talked about? Panel generation
Energy
factor.
loss in the system.
Then energy
Loss in the system.
Okay. So now energy generation factor is the same thing as performance ratio. As long as you're talking about now it depends on the scope. If you're looking at the solar PV, then it's the same thing as the performance ratio. Okay. But when you're not talking about energy loss in the system, you're not talking about the entire system, from the solar PV module to the inverter to the battery and all of that. So by the time this energy passes through all of these systems, there are losses along the line. There are losses everywhere. So by the time the energy is coming out to the metering point, all the losses is what we now classify as energy loss in the system.
Okay. Okay.
Is
That's
that clear?
fine. Yeah.
Okay. Yeah. So,
thank you.
okay.
Chima, let me also say it's just like in hydropower. When you are calculating the efficiency of a hydropower system, it will be the efficiency of the generator, the efficiency of the turbine, or the efficiency of the motor combined together will now give you the average efficiency of the system. Thank you. Continue.
Okay. Thank you, General. So let us look at the load profile. Now, load profile is a very important factor. It's a very important subject if you're to design a solar PV system. Now, this is the problem where a lot of people over design or you under design because you don't have an idea of what the load you're going to power. Okay. Now, remember, there's a difference between energy and power. Okay. Load profile deals a lot with power, not energy. Load profile deals a lot with power, not energy. So we'll talk about it. I hope we'll be able to wrap it up before our time. Otherwise, we'll continue tomorrow. So load profile. For a successful electrification project, it is necessary to conduct a precise analysis of expected electricity demand as it is significant impact on the design and cost within the project. Like I just said, if you don't know the magnitude of the load you want to power, then there's a problem. It's either you over design or you under design, and then either way there's a problem. So it's very, very important you do some level of energy and load assessment for you to be able to size your system properly. Okay, so we're going to spend quite a good number of trying to explain this thing, and then we'll be able to simulate some of this, so you can be able to have a clear understanding of how to navigate around them. So the system should neither be unnecessarily oversized or undersized. System oversizing leads to high cost. System undersizing could lead to dissatisfaction of electricity consumer due to unreliable electricity supply. I've had a lot of complaints. In fact, this is one of the reasons why people say that solar is not working, because they engaged the wrong personnel to do the design, construction, and construction of their system. Okay, or sometimes it could also be the problem of the person who is using the system. So someone can come to your house, and then at the time he was at your house to do a load assessment, you didn't have an AC, so he only provided a solar system that could power what you have. Okay, but by the time he's done with his design and construction and everything, you're happy. You can switch on the light and everything. Then you went and buy AC, and then you put it. And then you expect that system is going to power your AC and everything. And if there's a problem, you now begin to complain that the person has done a bad job. No, the person hasn't done a bad job. It is you who didn't understand how the system works. And then because of your lack of knowledge, you've made the system to fail. Okay. So it's very important here that even when you're doing this project, you need to consider future load. You need to talk to your clients. You design both for the present and for the future, depending on his budget. Okay, so it's important that they know and understand all of these things. So therefore, electricity generation and electricity demand should be in balance with each other. Supply and demand should be in balance. If there's the higher the deviation, then the higher the risk of unreliability, and also the higher the cost of the projects. Okay. So for this reason, demand analysis is required, leading to a creation of a load profile. So a load profile is a graph showing a variation of electrical consumption over time. The time span can be day, a month, or a year. A forecasted load profile with a minute-by-minute resolution on the time scale will be desirable, but usually it is not possible to predict demand within such accuracy. A load profile with an hourly resolution is a good estimate to start with. So what this means that if you have a meter that measures your power demand, not your energy, energy is different. Energy is kilowatt hour. Your power is your active power at a momentarily demand at the moment is in kilowatts or watts, depending. So if you have a meter and it measures your power in kilowatts, what this means that if you can keep record of every minute you look at it, you record it every minute, not even minute, yeah, okay. So for the purpose of this, the write-up I have here, if you keep recording it every minute for one day, then it's good enough for you to predict the time when you're going to be consuming the highest amount of power and the time when you'll be consuming the lowest amount of power. So what that does for you, you can say, okay, the time I'm consuming the highest amount of power, because I don't have enough capacity to cover it, let me move some of those consumption from that high point to the lower point. These are part of the knowledge you can get from such load profile graph. But however, to do that, it's tedious, it's a lot of work. So if you can get a daily profile, maybe average, every day, what's your average kilowatt? Or even maybe every hour, what's the average kilowatt? That might be enough. So just for us to have a pictorial view of what it looks like. This is what a load profile looks like. The figure load profile on a simple day shows an example of an hourly demand. Now this is an hourly demand, okay? Coming in a load profile for one day. So this is what a load profile for one day will look like. So you find out that this is 1 a.m. at midnight, 2, 3, 4. As the day begins to break, 7, 8, their power begins to increase. Okay, it begins to increase. Okay, at about 3 or so, it drops slightly. Okay, and then increase. Then at 19 o'clock, which is about 7 p.m., that's when they had their peak. At that time, almost everybody, the light bulbs are on, the TVs are on, almost everything is on at that time. So that's when they have their peak. But as time goes, maybe some of them start going to bed, okay, and started sleep, and then the power begins to drop. So this is what your load profile looks like on a sample day. So now, if you compress that and then extrapolate it for a month, yeah, this is what it's going to look like. So the figure load profile for 1 month shows that the load profile may change on daily basis. So this is for 1 month. It's almost similar, but some certain days you find out that it has a higher peak than other days. So this is what a load profile on a monthly basis looks like. So if you're designing a solar PV for this kind of load profile, your solar PV must be sized to be able to accommodate this peak, this consumption here, which is the highest. Your solar PV must be sized to accommodate it. Okay. So the problem now is that at this time, when you have this kind of peak, you have a lot of redundancies. You have a lot of capacity of the solar panel that are not being utilized because you just have, just a few minutes of or an hour of consumption, that actually uses this high amount of power. So you can actually gain from the knowledge by shifting the load at this point to some other point. Perhaps it could be that maybe your pumping machine is running. It could be that your washing machine is running. These are loads that you can vary. You can actually shift their demand, and then you can then reduce the size of your PV design. So I have explained this already, talking about your peak. So an important point in the load profile is the peak load. The generator in the system must be able to deliver the peak load and adequate additional reserve power. The figure shows a peak load in a sample day occurring at 7 p.m. in the evening. The peak load describes the maximum load or electric power consumption within a certain period, e.g. in a day or in a year. I already explained it. This load is significantly higher than the average supply level. Its occurrence during a day or a year depends on consumption pattern, types of consumer, whether household, industry, commercial, or whatever, and then your climatic condition. It is expected that during the hot weather, you're going to use more cooling load. And if you're using more cooling load, you're going to spike your peak at that period. So for an optimal analysis, the load profile should be generated for the complete year. Then the unit for the values of the load profile must be given in watts or kilowatt. Remember, I told you that this is power, not energy. Your load profile is generated in watts or kilowatts. So if seasonal variation of the energy demand are likely, all seasons should be evaluated regarding their individual load profile. Differing values for weekdays and weekends and weekend days must be considered too. In greenfield projects where an entire electrification system is built from scratch, energy demand can be estimated by listing all major appliances and multiplying each by the foreseen running hours. Now, this is more like conducting an energy audit. Now, the greenfield means that there's no building existing, but you're planning to build a house. So you can then begin to ask questions. What are the loads? What are the things you're going to, what are the electrical equipment you're going to put in this house? How long are you going to use them? By doing so, you'll be able to produce an estimate of what their load profile should look like. Also, you can also compare similar buildings. If, for example, there is a factory that's going to be producing polyethylene nylon, you can also try and see if maybe there are existing polyethylene nylon factories, and then look at their load profile and then compare and have an idea of what the load profile would look like. So in that case, you're trying to benchmark. So we've looked at load profile, and let us look at how you can be able to integrate your solar generation, your solar energy generation into your load profile. So we're going to look at the integration of solar generation profile into electricity demand profile. So normally on a good sunny day, this is how your solar PV will perform. Okay, the sun will come out around 7 and it will die down around 6. It will get to its peak around 12:01. Okay. So assuming that this is a 8 kilowatt peak solar system, so you find out that the solar system did not hit 8 kilowatt because of losses, the performance ratio. That's why you have this gap here. So this is the highest it's able to do. So on a typical sunny day, this is your solar generation profile on a typical sunny day. Now, for the purpose of simplicity, every box that you see here is equal to 1 kilowatt hour. Every box you see here is 1 unit of energy, 1 kilowatt hour. That's what everybody. So if you want to now calculate the amount of energy that this solar system has produced, you count all the boxes in this region, then that will be able to tell you the amount of energy that the solar panel has generated. Now, this is for illustration purpose only. So this is a typical load profile. I've shown you how the profile of solar generation look like. Now, this is a typical load profile on a typical day with a maximum load of 10 kilowatts. Okay. So what I'm going to do, I'm going to impose that solar PV profile on this load profile. So what this load profile tells us is that on daily basis, this facility consumes 163 kilowatt hours, 163 units of energy. If you check that by month, you have 4,900 kilowatt hour of energy. So, but we don't want to cover all of this energy by the solar system. So if you integrate that solar system into this, remember, it is 8 kilowatt peak solar system. If you integrate it into this system, it becomes a very good design because your peak is around 10 kilowatts, and then your solar is doing just about 6. And so whatever the solar PV module is able to generate is consumed. Now, what will make a bad design is when you now go and install 20 kilowatt peak solar panel in this house. Maybe because you see that their peak is 10 kilowatts, and you now go and install 20 kilowatt peak solar panel in this house. It will become a bad design. What is going to happen is this. During this sun hour, the solar generation will shoot beyond their energy demand. It will shoot above this, and then it becomes wasted, assuming there is no storage, unless when you have a storage. But assuming you don't have a storage, because in this case now it's without storage, okay? So when you do that, you overshoot their demand, and then it becomes over-design, okay? So that's why it's important you understand their load profile, and then depending on the configuration you want to do, whether you're doing with storage or without storage, it is always important that you understand their load profile. So this is a load profile with a 8 kilowatt peak solar PV system installed. Now this is another configuration. In this case, you have sorry. Okay, so in this case, it's a simplified daily demand profile with 10 kilowatt peak. You know, in the previous one, I had 8 kilowatt, but in this case, we have 10 kilowatt peak. Okay, so what you will notice that during the day when the sun is shining, that it actually generated more than the demand. Okay, so this will make a bad design unless whereby you are connected to the grid or you have a battery storage system. So if you're not connected to the grid and you don't have a battery storage system and you produce this kind of demand, then you've wasted the resources in this case. You've wasted the capital in building this kind of project. So all the energy that have been generated higher than their demand at this time would be wasted. But if you're connected to the grid, just like you have in Germany, then you can fit this energy into the grid. Then it's not wasted, okay? So, but in this case now, we assume that it's connected to the grid. So you can actually fit this into the grid. Now, if we upscale it to 17 kilowatts peak, okay, then this is what we have. I want you to notice something. As you keep increasing the solar installation, okay, the more you keep reducing your energy dependency on the grid. Now, look at this chart here. You have 28% that you're feeding to the grid, and then you have 72 that you're actually using. You have 72% that you're actually using. Well, let us look at okay, let us look at this one. No, actually, the pie chart I want you to look at is this one here, not this upper one, the one here that has demand covered by, okay? So here, your demand that is covered by the grid is 67, okay? And your demand that is covered by the PV system is 33. But when you increase your PV size, you find out that your demand that is covered by the grid will drop, okay? And your demand that is covered by the PV system will increase. Now, notice that as you're increasing your PV system, your this pyramid is actually growing taller, and the base of the pyramid is actually meeting some of your needs. Now, look at what I mean. If you look at here, you see that the base of the pyramid is somewhere down here, okay? But if you increase the capacity of the PV system, then the base of the pyramid will increase, and it will then cover more of your energy demand at this point. But this is only viable when you're feeding the excess to the grid. If you're not feeding the excess to the grid and there's no storage system attached to your design, then this is an optimum design for you. So in this case now we still have 17 kilowatt peak, but in this case we will not have storage. Okay, so what this does is that when the production from the solar PV module exceeds your current demand, the excess will now be used to charge your battery. So during the night, you can now combine your battery with the grid, and then you can be able to reduce your energy demand from the grid. So this is what is trying to illustrate. So now this is on a cloudy day, okay? You still have 17 kilowatt peak, but in a cloudy day, now while you're designing, there's what we call days of autonomy, or cloudy day, or days when there is no sun, okay? So if you're doing your energy yield estimation for a whole year, you cannot assume that the sun must shine for 365 days. You must be able to give some tolerance. You can be able to estimate, okay, for 365 days, I'm expecting that the sun will only shine for maybe 250 days or 300 days, depending on the weather condition of the location where you're designing for. Okay, so it's very important. So this is just trying to illustrate a typical load profile and PV generation on a cloudy day. Okay, in as much as you have 17 kilowatt peak, the performance on that cloudy day is low. Okay, it's not even enough to charge the battery or sell to the grid. So this is synonymous to the first design that we have when I told that all generated energy from the PV system are consumed. So this is important just so that you know how to impose your load profile, your solar PV generation profile to your demand profile. Okay, it is important you know, you have an idea of the load you're powering, then you'll be able to now impose the generation from your solar PV to that load so that you don't oversize or undersize. So this is, we're going to look at how you can actually get rid of your generator backup, okay? Even though it might be capital intensive, but it's good you have the knowledge of that it is possible, and this is how it can be achieved, okay? So that's why I decided to put this section into it. So it's actually possible that you can eliminate your generator and then do your solar PV design, but that is where you're not integrating it into the grid. And it is very possible, the technology is already here in Nigeria. I know in one or two sites it has been installed and demonstrated, so it is working. So it is important you also have that knowledge. So this is a regular generator backup. So using the same load profile that we had earlier on, okay? So in this case, we have a generator size of 20 kVA, and they will have a solar PV. We don't even have a solar PV in this case. There is no storage. So it's just your generator and your grid. So this this gray part is the part that is being powered by your grid, and this orange part are the part that are being powered by your generator. So it is assumed that at this time, at 1 p.m., that the grid failed. So generator has to kick in and then provide the energy for this period. Then at this point in time again, 8 p.m., there's also grid outage. So your generator comes in and then provide the energy in this. So this is your normal generator backup system without PV. So now let us add grid connected PV into it. And the instruction is that this PV is going to disconnect during generator operation. So if the grid fail, now this is a grid tied solar PV system. So you put solar panels in your house, there is no storage. You have 17 kilowatt peak solar system in your house. You still have generator in your house. But the point is this: anytime the grid fails, whatever power that is being generated by your solar PV system has to be wasted. Because anytime the grid fails, your generator will just come in and then serve your load. So in this case, your generator is not combining the energy output from your PV system. That's what this slide is talking about. So in this case now, you have excess generation here, and you're feeding it to the grid. But at 1 p.m., the grid fell. There's a power outage in the grid. And once there's a power outage in the grid, your solar PV stops generating, your generator has to kick in and then serve the load at this point. Then at night time, because the sun is not out and there is a grid outage, your generator has to serve this load. So we want to progress from here. Now this is another section of it. Now at this level, you have the PV, but in this case, if the grid fails, your PV does not go out. Now there's what we call islanding in inverter. You know that if you have a grid connected PV system and you have an inverter, and that inverter is feeding to the grid, the question is, what happens when there's a grid failure? Okay, if there's a grid failure, or maybe there is the utilities, the distribution company decided to switch off the grid because they want to do maintenance. What that means that your solar PV will keep on feeding in the energy into the grid, which is dangerous. Okay, so there's what we call anti-islanding. It's a feature that is built in inverters. Okay, so that's anti-islanding. What it does is that anytime there's a grid failure, it automatically cuts your inverter from supplying power to the grid. Okay, so that is the case here in this section that I'm talking about. This system is installed with an anti-islanding inverter. Anytime there is a grid failure, it stops sending energy to the grid. Okay, but your house is still powered. It still supplies power to your house. Okay, so in this case, because the solar energy is not reliable, what this means that your generator must still run. I will explain this in a more detail when I begin to talk about hybrid system, how you combine your generator and your solar panel. But at this level, just know that your solar system cannot reliably supply all your required energy, because imagine that there is no generator, you're just running your solar system, and then there's a cloud that passes along your solar panel, or there's a shadow that passes along around your solar panel. What that means that your output from that solar panel will just drop. What happens if you have a critical load connected to that solar panel? It will go off automatically. Okay, so for that reason, you don't want your critical equipment to go off. You still need to put your generator on, so that should in case the output from your solar system drops, your generator can be able to continue and then cover that shortfall. And that is why it is important that even while you're having your solar system without storage, you have a generator backup. If you notice, we don't have storage in this system. So for that reason, your generator has to be on. So what that means that at this point, when there's a power outage, your generator and your solar system are supplying the load here. But at night, at 8 p.m., when there's a power outage, only your generator is supplying this load at this point. That's what this is just trying to illustrate. So now we are progressing to the point where you now add storage. If you add storage to this configuration, okay, so what that means that the excess generation from your solar system can then be used to charge your battery. So when during the daytime, when this solar generation profile exceeds your demand, the excess will now be stored in your battery. Okay. Now the reason why you will notice that you still have your, okay, in this case you don't have generator. There's no generator, and the reason is because you have a battery storage. So even if maybe there is a shadow on your solar panel during the day when there's grid outage, okay, if there's a shadow on it, the energy stored in your battery will quickly come up to meet up that shortfall. Okay, so that's why you no longer have generator here. Then at night, when there's a power outage for 1 hour, the energy stored in your battery can then be used at this point. So you will now notice at this point now, you've been able to successfully eliminate your generator, and then you've integrated storage system. But this has to be done with caution because storage is very expensive, and that's why it is still important that you still keep your generator until we achieve a breakthrough in storage technology. So this explains how you can actually eliminate the use of your generator by integrating storage with solar system and the grid. 3 sources: the grid, you're not neglecting the grid, your solar system, and again, your battery. If you integrate these 3 of them with a good control mechanism, then you can get rid of your generator. But again, you have to do a cost-benefit analysis to know if it's worth it or if keeping your generator makes more sense. So, but again, this whole thing will become more appealing when you integrate energy efficiency. In the last course before this one, we talked about energy efficiency in detail. Energy efficiency means reducing your demand, reducing your load. So when you reduce your load, what that means that you're going to have more storage, you're going to have more energy stored in your battery, and you're also going to reduce your system size. You'll find that instead of installing 17 kilowatts, you can actually reduce it to maybe about 15 because you've dropped your demand from this point to this point. Your peak demand from this point, which is about 10, to this point, which is about 8. Okay, so you can then reduce the size of your design, and when you reduce the size of your design, you actually save money. That is the impact of energy efficiency in solar PV design. So more importantly, you find out that you have your battery storage, but again, you can actually reduce your battery storage because of nighttime. You can notice that during the nighttime, you need to power all this load with battery. But what if you can shift the load here? I mean, this load, I mean, if there's a power outage at 8 p.m., instead of your battery powering all the demand here, what if you can switch off some of your load? So for example, if you can switch off your air conditioning system, if you can switch off your washing machine or your dishwasher or whatever it is, just to reduce the consumption here, just for 1 hour, after 1 hour or 2 hours, you can actually use some of those things. So it is important that you know some of the load that are variable, that you can vary their use. So for example, ironing, your ironing clothes, you can actually decide not to iron at this time when your system is running on battery, and then decide to iron when the power, the grid is restored, or vice versa, or even when the sun is out. So this is what we call prioritizing load. If you do this, you'll be able to reduce the cost of the solar system, whether the storage or the PV system. So all these are benefits of energy efficiency and load shifting in your design. You can actually communicate all of this to your client when dealing with them. So now this is just a worst case scenario. I mean, in the day that the sun did not come out very well. So if you're designing, normally you have to take into consideration the day that the sun is not going to come out, and then you size your battery to be able to supply the energy that is required for that day. Okay, but imagine that, okay, the day that the sun did not come out, and imagine there are loads that you can shift. Imagine that there are appliances that you can avoid to use on that day. What that means is that you can actually reduce the size of your battery, okay? And when you reduce the size of your battery storage, you're definitely going to save the cost of that project. You're going to reduce the cost of that project. So all of these are very, very important, in your design. And that's why, you remember when I was starting this training, I talked about the 2 pillars of sustainable energy development, and I talked about energy efficiency, then I talk about renewable energy. Now you're beginning to see how energy efficiency is coming into play in all of this. So we've come to the end of this training today, and I hope you did enjoy it. If you have questions, please, you have my contact. You can always reach me anytime. Your questions are not limited to this session. From now onward, you have my contact. You can always reach me if you have further questions. If you have a project and you feel that maybe something you don't get clear and you might want some certain clarification, you can always reach me. You can always reach Engineer Uche. We are always available to support you. Thank you very much for your time. Engineer Uche.
Yeah, thank you, Chima.
Okay.
Actually, I had to switch to my mobile.
Okay.
I think
we didn't actually take the picture. Is this something we can do now?
Yeah, you have to do it because you have control. So please, gentlemen, I want to grab our indulgence. Can we just put on our camera? I know our time is fast spent. Even me, my camera cannot come on because iPhone says I must give permission. Those that can, please, let's just put in. My logo is already let's just put on our camera. Chima, you can take it. I think I have to exit. I'm using mobile because of network issues.
Okay.
So as many people just do screenshots, snap screen.
Just a moment. Let me.
Meanwhile, let's prepare our questions. I think we still have a sizable number of people around.
Can we have more people to switch on their camera, please? This is
just for 1 minute. Just for 1 minute.
A good number of people have not done that.
If we can have a 50% shading.
Yes. No, they're responding. No, they're responding. They're responding.
Yeah, somebody says Zoom unable to take camera. Yeah, mine too. My iPhone is telling me to give permission. And if I go leave this
Okay.
place now to take off.
Okay. Okay.
So just take it anyhow. Maybe by tomorrow we'll take a more formal one. Tomorrow I will
Okay.
work on my I use Airtel and Airtel is messing up.
Okay.
Okay.
Okay. That's good.
Okay. One thing you said that I really took cognizance of is the idea of energy efficiency. I think that is the idea of the energy auditing training, because the more energy auditors we have in Nigeria, the more the awareness. Because what we need to do, we've tried over the years to increase our energy, to have more energy balance, to have more energy generation. Since we're not making progress, then it's better we go into energy efficiency and energy, but which you have to achieve by auditing your energy anyway, so that the little 500, 400, 5,000, 400,000 megawatts, which has dropped to 3,500 as of yesterday, we can be able to start to manage it, micromanage it. Let me use that word. And just like you said in your last slide, the knowledge of this also has a personal implication. When you have knowledge of some of this renewable energy knowledge and energy efficiency knowledge, it will help you in your own personal life. For instance, if you go to buy AC, for instance, you should be able to buy an AC that is energy saver. If you're the type that enjoy buying old ACs, you should stop it because it doesn't work. Because at the end of the day, you end up paying more. Or the television, you want to buy television, you need to go for energy savers. Or you want to go for some appliances in your house. Knowledge of energy efficiency will guide you. It's not penny wise, pound foolish. You might get it cheaper, but in the long run, you spend more. That's why I see some of these Europeans coming to dump things in Nigeria because they know they don't need it anymore. And we will think we're buying it cheap, but they are ripping us off. It's ripping us off on the long run. By the time you sit down and do the cost saving, which we'll do in the next training, you'll be able to see how you can save cost and then reinvest. And then you achieve a kind of a net positive investment or net MPV. So Chima, thank you for that enlightenment. The training today is not just about increasing our professional knowledge, but also has a personal touch. Our time is fast spent. I think we've been able to cover the time we spent waiting for people to log in. Tomorrow is Friday, and 3 o'clock we'll start all over. We'll start again for the second phase, which I know I already have an idea of what it's going to be. Part of mini grid and the continuation of where we stopped today. So once again, if there's no other question, I'm going to be ending the class. Chima, please, can you pause the recording?
Engineer, hold on. I just want to respond to a few comments I
saw.
Yeah,
but the recording, you have to pause the recording. You have to end the recording.
Stop the recording. Okay, I just stopped. Okay.
Yeah, stop. Yeah, not just pause. Yes.